So it's a pleasure to be speaking to you this afternoon about practical sandboxing on the Windows platform. And this is essentially an assessment of the kinds of security benefits we can get from the sandboxes used by Protected Mode Internet Explorer, Adobe Reader X, and also Google Chrome and the Chromium project. So if I can just introduce myself, my name's tomkeetch. I work for Verizon Business's Threat and Vulnerability Practice, and I'm the lead consultant for code review within the EMEA region. So I've been presenting on this and kind of similar topics for a little while now. It started when I wanted to look at protected mode IE and try and answer the question, well, how much safer is this making me? What additional protection is this really giving me? And from what was publicly available from Microsoft, it was kind of unclear. So then I kind of expanded my remit to looking at practical sandboxing more generally and incorporating these different sandboxes. So this is going to be an attack-focused presentation. Other previous presentations have maybe been, so the OS one was maybe more defense-centric, and each presentation has got a different focus, so I'd encourage you, if you're interested, to go back and look at some of the previous white papers and so on. And why am I speaking about this topic? Well, exploit mitigations are, to me, extremely interesting. They're my favorite topic. And it's basically trying to answer the question, how do we make finding and exploiting vulnerabilities prohibitively expensive for attackers? We want to dissuade them from attacking products that we design. We want to dissuade them from attacking other consumers or particular customers and make them go after harder targets. So so I want to give you a very brief introduction to what practical sandboxing is. I won't go too deep into the mechanisms behind it, but if you're interested, there's a lot of further reading and a lot of other people that have presented on that topic. So what is practical sandboxing? So it's a way in which applications can create their own customized sandboxes for their applications using entirely user mode components. So if you take a kind of a generic sandbox like Sandboxing, that's typically using kernel drivers. Now we don't want to have to ship kernel drivers with our browsers or with our PDF renderers, not least because if there's a minor bug in our sandbox implementation, it's going to take the whole system down. And so practical sandbox is a methodology, a collection of techniques that can be brought together to provide a reasonably secure user mode sandbox. And so it's based entirely on facilities provided by the Windows operating system. This is going to focus on three main consumers of this methodology. So Protected Mode IE, which has got a very limited implementation, and Adobe Reader X and Chromium that have got more complete implementations. There are some others, like the Microsoft Office isolated conversion environment, and there might be some other consumers that I'm not aware of, but I don't go into detail on those. So really what this presentation about is not only what are these sandboxes, but how can we escape from these sandboxes with a minimum amount of effort. I'm not a vulnerability researcher. I was looking at this from maybe a higher level and trying to find vectors and simple exploits that I could use to escape the sandbox. So the presentation can be structured like this. So I want to begin by kind of giving a framework to work within to try and give a context to the kinds of issues that I found and try and explain why these are important. Then give you a brief background on the practical sandboxing implementations themselves. There's going to be a number of the practical content is a number of vectors and exploits that can be used to escape these sandboxes today, and all of these are still valid. And I think every presentation should have maybe an argumentative part, and so that I'm going to be kind of deconstructing Adobe's own view of the sandboxes and exploit mitigation, and saying, well, maybe they're being a little too charitable about how effective this really is. and then hopefully you can draw some conclusions that not only apply to sandboxes but to exploit mitigation in general, which is, I think, is becoming a more and more important topic. So, sandboxes for exploit mitigation. Why would you use a sandbox for exploit mitigation? So, when trying to mitigate against a particular exploit or a class of exploits, we've got two main options for designing that. So either we can look to increase the cost of exploitation, and this is done very effectively by combining DEP and ASLR. As we've seen with Peter's presentation earlier on Mona, this is essentially an arms race, because each time these new mitigations come up, ways come about of bypassing them, and as attackers mature, they can bypass these more and more easily. But they still serve us well, because they force attackers to focus on less generic exploitation techniques. And so typically exploits have to use a kind of application-specific exploitation technique, such as, for example, JIT spraying. So sandboxes work as an exploit mitigation by reducing the value of compromising a target to an attacker. So by placing a process inside a more restrictive environment without access to privileged resources, we make it a less enticing target. But none of these exploit mitigations are perfect. Normally the sandboxes themselves have implementation flaws or ways in which they can be bypassed. So we assume that any sandbox can be bypassed for some finite cost. That might be very high or very low, depending on how good the implementation is. And this presentation is a focus on the sandbox escape part of that. So once you've got our malicious code running inside a sandbox process, how can we escape that sandbox? It's far too much to squeeze into just an hour, so I'm more than happy to take questions either at the end, or you can contact me over Twitter or email. So I want to introduce a concept of return on exploitation. So whenever someone wants to attack a system, ultimately, if they're financially motivated, they're looking to gain something of some value to them, and that value would depend on the attacker. And there's also kind of an expected cost to developing and deploying an exploit. So when we want to escape a sandbox, typically we've got a two-step attack process with potentially two separate exploits and kind of two separate, payoffs. So there's the cost of the initial exploit. So that would be a typical remote exploit that will get you code execution, and then there's the cost of developing the exploit that escapes the sandbox. And so one of the things I've focused on here is trying to find the cheapest way to escape the sandbox. So an attack is only really viable if the expected payoff, which is a two-step, is greater than the expected cost of developing that exploit. So in terms of exploit mitigations, there are two ways in which this can kind of fail. Firstly, we can bypass exploit mitigation, and that's going to have some variable costs associated with it. But if the exploit mitigation is trivial to bypass, we just have to modify our attack slightly, and it will work just as it did before, and so it won't be dissuading any of our attackers. Or it could be that what we're trying to protect has such a high value that these kinds of exploit mitigations aren't really effective, because although they're making it harder, they're not dissuading attackers from going after these systems necessarily. Or the second failing, which is more relevant to sandboxes, is that it doesn't reduce the value of a remote code execution bug for a particular application. So either the sandbox is protecting the wrong assets, or they're assets that actually just can't be protected by a sandbox. So depending on the type of application, it might be that a sandbox is completely pointless. So there's four cases. So case A is what I would call kind of a safe system. So this might be that it's extremely secure, or it just doesn't have a very high value to an attacker, and the expected cost of developing and deploying an attack is always higher than the expected payoff from successful exploitation. Likewise, B is an unsafe system. It's always going to be, there isn't really adequate exploit mitigation in place, and so the payoff is always positive for an attacker. Cases C and D are the two failure modes that I talked about on the previous slide. So case C is where it's an exploit mitigation that's trivial to bypass, and case D is where you've got an extremely strong sandbox, but you may be protecting the wrong thing. So even without bypassing the sandbox, you're still gaining access to all the resources that are actually your objective. Okay, so this was focusing on looking on cheap exploits, and I hope that's kind of framed the argument to show why this is important. So as a result, I found a number of kind of exploits and vectors. These kind of fell into 3 or 4 categories. So the first was previously unexposed interfaces. By introducing a new security boundary within an existing system, actually you might be exposing new interfaces that weren't previously subject to having malicious inputs sent to them. Also, there are particular easily detectable and exploitable conditions that might easily allow sandbox escape. But actually, most of the bugs are due to incomplete implementations. So various implementations didn't implement the entire practical sandboxing methodology, and as a result, they're vulnerable to specific classes of issues. And there are also some sandbox-specific issues which relate to the particular sandboxing architecture or design that's in place. There are also a number of resources which aren't protected by practical sandboxing. So network access is unrestricted, so you could go on to attack other hosts on the network. Anything, in the case of browsers, anything that's protected by the same origin policy isn't going to be protected, so you can steal someone's cookies and so on. And also, any bugs in kernel interfaces are still exploitable to escape the sandbox. Okay, so it's an overview of how these sandboxes are implemented. So the practical sandboxing methodology brings together kind of, depending how you measure it, 3, 4, 6 different mechanisms. So the main one is the use of restricted access tokens. So every process, every thread has got kind of a set of permissions, a set of access rights associated with it, and maybe a set of group memberships. So the first way that we can limit what a process or a thread can do is to remove group membership SIDs from its token. So you might do this by removing the administrator SID and say you can only use this SID for denying access to resource, not for permitting access to resource. Sorry. And so that covers discretionary access control. We want to remove all of the rights associated with a process. And we can also mark something as being low integrity on Vista and later. So low integrity says this process is less trustworthy than a normal user process. And actually integrity levels enforce various checks throughout the system that kind of overlaps with a lot of these other mechanisms. So the use of mandatory integrity control or integrity levels isn't a necessary part of this methodology, but it's mainly used for defense in depth. We can also strip particular capabilities from a token, so remove the right to impersonate other users. So there's a completely separate set of separate access control mechanism associated with the GUI subsystem. So there's the concepts of Windows stations and desktops, and any application on the same desktop are essentially in the same security compartment. So we have to implement Windows station isolation and desktop isolation. And unfortunately, I don't have time to go too much into detail about those. And lastly, we can use job object restrictions. So job objects are used to manage groups of processes as a single unit. And there are actually additional restrictions that can be applied through job objects that are a necessary part of practical sandboxing. So they seem to have having a better time than we are. So each of these mitigates against a different attack, and actually by looking at the different sandboxes and figuring out what they do and don't implement, we can determine different attack strategies for the different sandboxes. So Protected Mode IE was the very first implementation, and it chooses to run to render sites in lesser trusted IE zones at low integrity. And low integrity is the main way that it segregates things from the rest of the system. Otherwise, they share in the same session, WinStation desktop, and of course, any websites which are in more trusted zones aren't sandboxed. So if we look at this kind of as a checklist, so really they implement low integrity and some basic privilege stripping, but they're mostly kind of overlapping mechanisms anyway. So this is a very, very limited implementation. As a result of using integrity levels, so this sandbox only works on Vista and later. It only protects the integrity of a system, so preventing the modification of files, and it doesn't protect the confidentiality. So as a kind of a simple failure of this sandbox is that a compromised IE process can read all of a user's files and send them back to their remote server because network access isn't restricted. And they've got full access to things like the clipboard and also the global atom table, which is a primitive form of IPC, and that actually exposes other applications to certain types of attacks through this interface. So I presented this research at Hack.lu, and this was kind of my first kind of foray into kind of talking to other people about this research. And I presented a number of different ways in which you can escape from this sandbox, including through UAC launches, what I call trusted broker attacks, and I also presented a generic Protected Mode IE bypass that works on domain-joined workstations, and this, as far as I can tell, will not be fixed by Microsoft. Yeah, so they're saying this isn't a security boundary, so we're not necessarily going to fix any of these sandbox escapes. And just the sheer number of potential elevation routes means that actually they can't make any guarantees about how much safe you are with Protected Mode IE. Adobe Reader X implemented a much stronger sandbox. So they started using restricted tokens that didn't just use low integrity, and they started applying job object restrictions. But for various kind of reasons related to this legacy application, they couldn't implement Windows Station isolation or desktop isolation, and this brings about the possibility of various UI spoofing attacks. But there are also some other weaknesses. So if we look at this as a checklist, they're applying almost entirely a fully restricted token, apart from one minor caveat, which actually results in a bypass. Yeah, and they're applying some, but not all of these job object restrictions. So it's actually making use of Google Chrome's own sandbox because it's using the same framework, because it's BSD licensed, and this framework provides it with does all the heavy lifting of locking down processes and also doing inter-process communication between the sandbox process and other more trusted components. So it's only the PDF renderer that's actually being sandboxed because that's the highest risk component. And through IPC, it speaks to the broker, and the broker can perform any more privileged operations on behalf of the renderer, but applying a policy that still doesn't allow code to escape from the sandbox. So we're trying to keep the renderer functional, but while still limiting the impact of any compromise. The main limitations are, firstly, that the broker doesn't restrict read access, so similar to the problem we saw with Protected Mode IE. So again, you can read all of the user's files, pipe them off to your remote server. Again, not protecting the clipboard, not protecting the global atom table. The most interesting limitation, and it won't be clear to you why, but the restricted token includes a entity authority restricted SID. And this permits a type of attack I call base named object namespace squatting. And because it's not implementing Windows Station desktop isolation, there are certain attacks that are possible, but they're actually compensating with a number of kind of overlapping job object restrictions that do the same thing. If you're interested about kind of those limitations, then I recommend the Adobe the Adobe Asset Team blog post on the topic. But obviously, take what they say, but a pinch of salt. So Chromium actually introduced a far more compartmentalized architecture. So each browser component is in its own individual sandbox. Now, if we look at the renderer sandbox, which contains WebKit, and as you know, that had a large number of remote code execution vulnerabilities in it, that's actually running in a very restricted sandbox. But then each different plugin can run in a different sandbox. So if we just look at the renderer, then actually we're seeing they're implementing the full practical sandboxing methodology. So they can't limit network access, and they can't prevent local kernel exploitation, but otherwise they're protecting themselves against everything that they can using this methodology. Yes, so they're using this framework which they've made available to other vendors, and that allows them to apply the full methodology. The renderer, and this is important, that is in the most restrictive possible sandbox. So any escapes from that would be either due to an implementation fault in the broker or various things that they can't protect against. Third-party plugins are often just not sandboxed at all, so like Shockwave Java, they all run fully unrestricted. So all of your Shockwave exploits still apply. And this was a source of confusion for maybe a famous French grey/black hat organization called Vupen. Adobe Flash has got a very, very limited sandbox. And also the GPU process just isn't sandboxed at all. And that's what kind of regulates how renderers communicate with like 3D graphics acceleration. Okay, so I think it's worth pointing out, because hopefully at the end of this presentation you'll all understand this much better than Vupen do. So they kind of opened the firing shot. Sorry Google, we just pwned your sandbox. And I was really excited when I saw this, because I thought, wow, they've really done something exceptional, I think. But no, Google actually all they had was a Flash exploit. But they kind of do have a point in that they've pointed out that if you have a Flash exploit, the Google Chrome sandbox can't protect you against it. But that's a very different thing from saying that they actually pwned the Google Chrome sandbox. So if we look at the Adobe Flash sandbox and we compare it to everything else, we actually see that actually isn't much of a sandbox at all. So it's a sandbox in a very, very limited kind of way, and this was kind of an initial implementation that they're kind of using as a stepping stone into implementing a full sandbox in a future release. And so if you remember, I said that any process running on the same desktop is running in the same security context. Well, so the simple way to escape this is to use what was called a shatter attack. So you can just send a message to either the broker or some other process and say, here, run my code, and then you've escaped the sandbox. So this really was not a very sophisticated... so they probably came up with a good Flash exploit, but as far as a Google Chrome exploit goes, what they said was highly misleading. Okay, so now I just want to kind of enumerate kind of a selection of cheap exploit vectors. So when I started, I wanted to say, show me what the easiest ways to escape are. So the first one is what I call local BNO namespace squatting. So the BNO namespace is a namespace that's shared between all the processes within a single session. And here we can have named objects such as shared sections and synchronization objects, and these can be referred to by other processes running in the same session. But by creating one of these named objects before another process, we can actually set the permissions on that object that's then going to be opened by another process. So if we weren't allowed write access to an object, and then we can squat on it and set our own permissions before the main process, before the kind of legitimate owner, then we can unexpectedly gain write access to something that we shouldn't. And this exposes applications thing. So there's 3 requirements for being able to perform this attack. First, you have to be able to create it before the application. So shared sections are the most interesting example because they allow us to basically input data into the application. The application creating the shared section shouldn't fail if the object already exists, and normally they don't. And then finally, we have to be able to predict the name of the object in advance. So then I found out that I could actually use this technique to escape protected mode IE generically. So this works today. Microsoft haven't yet fixed it, and although some of the steps won't be obvious because of all the background that I've skipped over, this is essentially the process. So the sandbox process can actually terminate the Internet Explorer main process, and then by predicting the process ID of the next process to be created, and then creating a name shared section which incorporates that process ID, we can put malicious data inside that shared section, and then the next time that IE starts up, a local remote code execution exploit will allow us to execute code within the context of the fully trusted IE process. We can use this to escape. So I didn't spend months and months and months looking for this vulnerability. I found a vector, wrote this fuzzer, which I'm not sure it could be any simpler. So all it does is create a shared section, takes the existing contents that are known good, and then it randomly changes bytes to random values. It's not doing anything clever at all, and so this is, and this found a bug within a day or something. So by kind of focusing my effort in the right area where I knew it was going to be weak, I could write an extremely simple fuzzer and find a bug that would generically bypass IE. So Microsoft's response was pretty disappointing, to be honest. They said, "Hey, great, you found this code execution vulnerability. Yep, this is definitely a vulnerability, but we're not going to fix it." Why? Because they're adamant that protected mode IE isn't a security boundary. So if you thought that trying to escape from protected mode IE was supposed to be difficult, then once you've got one bug, you can rest assured that Microsoft probably won't fix it until the next major release, which is kind of nice. It means I don't have to find any more bugs. And actually, this got Adobe's goat that they wouldn't fix this because it actually had an impact on their sandbox, which I cover on this slide. So this is exploitable in protected mode IE because they're only using integrity levels to isolate, to sandbox the process. But because Adobe Reader X has this restricted SID within its token, that actually allows the sandbox process to create objects inside this BNO namespace. And so this same vulnerability can be used to escape either Adobe Reader X or protected mode IE, but not Google Chrome because they're implementing the full methodology. So the fact that Microsoft won't fix this bug kind of allows another sandbox to be compromised. Okay, so a second exploit is Chrome specific, and actually it's an architectural issue that which I think will maybe be fixed in the coming year or two. But it's related to how they use NPAPI, which is the plugin interface, originally designed for the Netscape browser. So in the Netscape browser, plugins and early version of Firefox, plugins ran inside the same process as the browser. They weren't separated. There was no security boundaries between any of these. But NPAPI was used kind of in process. So then they were like, well, Adobe Flash keeps on crashing, and it's crashing my browsing session. Let's put it in another process, and then when Flash crashes, it won't take down my browser. So this is fine. So we get improved stability, but because none of these processes are sandboxed, there are no security gains. So the problem happens when actually we sandbox the browser tab, and we don't sandbox the plugin tab. So we originally had this interface that was used in process, and it's now being kind of reused in a inter-security context situation. So previously, an NPAPI caller, they mutually trusted each other because there wasn't a security boundary between them. But now we've got a sandbox process which is less trusted. We can now no longer assume as a plugin that people calling into our plugin are trustworthy, and they might try and send us malicious data. And so any exploitable bugs inside this, which weren't previously security issues, only stability issues, these bugs will actually allow sandbox escape. And you can kind of think of these bugs as kind of like implicit calling conventions. So it's like, I can trust someone to not supply null because they know that that's kind of the rule. So a good example of why this is kind of a real tangible issue is that I had a quick search through the bug database, and I found this particular issue. So a thread is crashing inside a mem copy with an access violation. So buffer overflow, anyone? This was never a security issue, and probably this code is about five years old, if not older. But the point is that these kind of previous bugs which weren't looked at in kind of a security light now become security relevant because they can allow code to escape the sandbox, which was never previously an issue. And this bug was fixed by Adobe, not by the Google Chrome team. And so these kind of implementation flaws in plugins in the NPAPI interface are actually quite difficult for Google Chrome to protect against. Also, you have the situation where the sandbox process can send key events to the plugin, and this is kind of a natural feature of the NPAPI interface. So I can say to Flash here, I just pressed the A key, I just left-clicked here, whatever. So you can actually use this to bypass Flash security dialogues from inside the sandbox, because the plugin has got no way of telling whether or not a key press or a click came from the plugin or from malicious code running inside the sandbox. And hopefully this will be fixed in the next generation plugin interface, which has been codenamed Pepper. So another kind of class of issue is handle leaks, and these affect every sandbox. In fact, any time where you've got two processes communicating. Yeah, sorry, I messed with that. Yeah, so a handle is basically just an opaque reference to a resource that's already been opened. So when you open a resource, you say, I want to use this resource for these purposes. And so every time you use that handle, if you're only using it for the purposes that were originally requested, there are no further access checks. So if for any reason you get a handle to certain types of resources inside your sandbox, then the entire sandbox breaks. And these are particularly interesting because we can easily scan for these handles at runtime. So what causes these handle leaks? So four main ways. They can be deliberately granted by the broker. So this might be a kind of basically a design limitation, in which case the sandbox just doesn't work. They could be accidentally granted, or through some kind of exploiting a logical error in the broker,
or even they could be incorrectly granted. So the broker is working correctly, but the policy is configured such that the sandbox boundary is no longer enforceable. But how these sandboxes normally work is that they initialize a process in an unrestricted state. They look at all the resources they need to pull together, and then once they've done all that initialization, they lock down the process and say, we've locked down the process, it's in a known good state, there's no malicious code here yet. And so actually, if any handles are opened during the initialization process and they aren't closed before the browser is compromised, then these handles can be used to escape. And these handles might be internally kept open by third-party libraries. There might be hook DLLs that get injected into the process and undermine the sandbox. And so any libraries which you use must be kind of sandbox friendly. And I guess the sandbox designers have to be aware of what types of libraries they're using and which ones are and aren't suitable for use. So an excellent example of the kind of problems that we can see is demonstrated by Adobe Reader X. So actually from inside the Sandbox PDF renderer, you've got read and write access to the user's cookie store, which is used by sites in the trusted zone. You should never have access to this handle, but the reason that it does is that when the process initializes at medium integrity and it loads the WinINet library, WinINet kind of internally opens up the shared section which allows you to read and write cookies. So this isn't really a security issue at the moment because the Adobe Reader X broker allows you to request read access to any file. So, it's not an issue at the moment. But if they do lock down their broker, then they're going to have to replace WinINet or change how they load it. And then there is a fourth option. So kind of a fourth vector, which is actually using the clipboard to attack other applications. This is just kind of a new attack vector that comes out of having these kind of incomplete sandbox implementations. So this clipboard is actually shared between every process in a user's session. So if you're using protected mode IE and if you ever have your password in the clipboard, that's generally not a good idea with these types of sandboxes. But what about actually attacking other applications for code, looking for code execution vulnerabilities? So from a developer's point of view, he's got not being aware of these sandboxes, maybe when the application was written 10 years ago, just a normal desktop application, they're implicitly trusting clipboard contents, because why would a user put malicious content into their own clipboard? It just doesn't make sense. So now clipboard contents aren't trustworthy with the Adobe Reader X and the protected mode IE sandboxes. Just a simple example of how this can be used for code execution. If you put a command line followed by a carriage return into the clipboard and then you paste it into a command window, it's going to execute. So that is a simple exploit, but maybe one that's not that likely to happen. I don't think many people know the shortcut for doing a paste into a command shell. Actually, who does out of interest? No, it doesn't matter. So the question is, do application developers implicitly trust clipboard contents? And overwhelmingly, the answer is going to be yes. So this is just one vector. So the last thing I really want to kind of cover in this presentation is looking at Adobe's asset team's kind of view of the sandbox and how they think it makes Adobe Reader X a lot safer. So actually speaking to some of the Adobe guys, they're like, we know it doesn't make us that much safer, but we're a lot safer than Adobe Reader 9. So they've seen very few attacks against Adobe Reader 10 because there are so many other people using Adobe Reader 9, which doesn't have the sandbox. But maybe in the future it's going to become a more interesting target. So they kind of had a blog post about how this sandbox was going to be awesome, and this was kind of their view of
what exploitation looks like now in Adobe Reader X. And they said, look, this is like a 5-6 stage process that's going to be really difficult for an attacker. And this is a big step up from maybe the 2 or 3 steps that you had to go through to exploit something without the sandbox. And so this is covered in the asset blog posts. So the first kind of counter argument to this is, well, if you're executing code on someone's machine, Adobe's already lost, and actually Adobe are kind of notoriously bad for saying, we've got a sandbox, it's a code execution, but they're not escaping the sandbox, so it's probably not that dangerous. But you can still go on to attack other systems on the same network, and so on. And of course, you can read all of a user's files. So this is still a remote code execution without sandbox escape is still a high criticality issue. The second kind of counter argument is that they're kind of saying that you've got to bypass DEP twice because you've got 2 code execution exploits. Again, this isn't true. DEP is not effective without ASLR. And if you're using a local code execution vulnerability, then ASLR isn't effective. So as a simple example, you want to be able to predict the base address of a DLL. But if you load the same DLL in your own process, it's going to have the same base address, like 95% of the time or more. So ASLR isn't effective, and therefore we can bypass ASLR in DEP. And also it's been shown that things like GS cookies are less effective because many of the entropy sources are actually locally available, things like the system clock. Again, you can't protect against local privilege escalations. So if you're going to pop a box and then go for a kernel exploit, you actually don't care whether or not you're in a sandbox at all. And this was the main reason that the Google security team were looking at Windows kernel exploits. So Tavis Ormandy and Julian Teen, they had a presentation not so long ago called "There's a Party in Ring Zero and You're Invited," and that was basically specifically addressing this threat, which they knew that the Google Chrome sandbox couldn't actually protect against. So, what conclusions can we draw from this? Hopefully you agree with these conclusions, but I think it's probably a good topic to discuss. So, firstly, actually the developing sandbox escape vulnerabilities varies hugely between implementations. So for protected mode IE, given that they won't actually fix these bugs, it's relatively easy. And then for Google Chrome, it's an order of magnitude harder. The secondary exploits that we'd use to escape the sandbox are a lot cheaper to find and exploit than the initial remote exploit. So this isn't necessarily if we think back to the kind of the graphs I had near the beginning, this isn't necessarily a big disincentive for attackers. And if the attackers are looking to steal your Gmail account, well, they can still steal your cookies. So if the resources are inside the sandbox, then they're not helping you. So these sandboxes are only protecting you against a very specific set of threats, and how effective they are actually depends on the motivation of the attacker. If you only want to pay attention to one slide and you slept through all the rest, wake up now, because this is it. This is the practical slide that you should take home with you. Maybe pin it on your wall and point people to it. So at the top, we've got the Google Chrome renderer, which is the strongest sandbox using this methodology. That's followed by the Adobe Reader X sandbox, and then that's followed again by protected mode IE. Importantly, for the VUPN exploit, the Google Chrome Flash plugin sandbox is even less restrictive than protected mode IE, which we've already said is the least, the sandbox that gives you the least protection. And then below that again, we've got things like privilege stripping. So, that kind of be things like removing administrative access. And so, what I really think this all means at the end of the day is that these sandboxes have changed how people look at exploitation, or at least I hope they have. there's going to be a greater emphasis on kind of local privilege escalation vulnerabilities. And actually due to these incomplete sandbox implementations, the desktop applications themselves might come under additional scrutiny if these incomplete sandboxes are going to kind of continue to be used. And this is because new attack surfaces have actually been exposed. Attackers will only start trying to escape from these sandboxes when they've really got cause to do so. There just isn't that motivation at the moment. If you've got 90% of people on Adobe Reader 9 and not 10, attackers are going to go after the 90%. And I really don't think that Adobe can rest on their laurels for too long, because at some point people are going to start attacking these sandboxes. Protect mode, i.e. sandbox escapes, only really became interesting to people and they started talking about them when actually Pwn to Own made it a requirement of Own. So I think we're going to see a progression where sandbox escapes become more and more common. So I hope that's kind of given you a good overview. I know that I skipped a lot of the kind of technical underlying content, but hopefully you can kind of appreciate the thrust of my argument. So I think we've got some time for some questions, or I'll be around afterwards and on Twitter and email if people want to discuss this in more detail. So any questions? No? Okay. Well, obviously I covered the material really well. If you do want to find out more, there is a whole wealth of other information which covers all the things I just couldn't fit into a 1-hour presentation. So yeah, thank you very much for your time.